All right, here's part 2 of the birthday paradox where we dive into probability. You ready? Here we go. Okay, so when we're talking about probability, we are talking about things that happen between 0 and 100%. So 0 is 0%, or it's never going to happen. Oh, so sad. Whereas 1 is 100%, and it's always going to happen. Cool. Okay, so now that we understand that, we can start to write equations that calculate the probability of a certain event. So most of us are pretty familiar with flipping a coin because coins have two sides. We can say that half of the time we're going to get one side and the other half of the time we're going to get the other side. Most of us are like, it's definitely biased because I always get heads. It's like, well, okay, sure. But if you were to flip the coin 10,000 times or more than that, you would find that it about evens out. You really do get heads about half the time and tails about half the time, assuming you're playing fair. Okay, so when we're talking about finding the probability with two people having the same birthday, we can write that like this, where P stands for probability. Probability of having the same birthday is 1 minus the probability of having a different birthday. And you're like, isn't that kind of cheating? Well, not really, because this is true. And also, this is way easier to calculate. So let's talk about that in a simple example. So what is the probability of someone having a different birthday? Well, if we only have one person, like if I'm in a room by myself and I'm like, does anyone have the same birthday as me? I don't have anyone to compare to. So the probability, there are 365 days, and that's it. The probability that we're going to find someone with a different birthday is, or well, I guess since there's no one, I will definitely not be able to find someone with the same birthday. If there are two people, then I multiply the probabilities together because we add them up. And the second person, if we're asking what is the probability that this person will have a different birthday, then the second person can have any birthday except for mine. So that leaves them with 364 days that they can have their birthday on. Because mine's unique. They can have my birthday. We're talking about different birthdays. When we have 3 people, the third person can have any birthday except for the birthday of the second person and the birthday of the first person. So that leaves them with 363 days. And so if we were to add these up and use a handy dandy calculator to figure this out, we would get, well, that just equals 1. So we're going to get 1 times 364 divided by 365 times 363 divided by 365. And we are going to get a probability of 99.2% that the 3 people will have different birthdays, which makes sense. If you only have 3 people in a room, it is very unlikely that they'll have a different birthday. So in that case, the probability that they have the same birthday is 1 minus this. So 1 minus 99.2% is sadly 0.8%. So the probability they have different birthdays, very high. The probability they have the same birthday, very low. But check this out. The probability of different birthdays goes down exponentially based on the number of people. And we can see that if we start writing this equation out and start coming up with a more compact way to write this. So let's just do a couple more terms. So if we have 4 people, that fourth person can have 362 days that they are able to have their birthday with it not being the same day as any of those first 3 people. And for the 5th person, we're going to get to 361 over 365. And then I'm going to write ... to indicate etc. Okay, so now we can start to simplify this and see if there are any patterns. So the first thing is that we can rewrite this, because it's multiplication, we can rewrite it as one big fraction. So we're going to get 364 times 365 times 363 times, etc., over 365, and the bottom is just 365 times itself a bunch of times. And so now I can say, okay, now that I have this equation, I can write this, I can simplify this by pulling out 1 over 365. And you'll notice that we multiply this by the total number of, we multiply 365 by itself. How many times do we do that? Well, the number of people in the room, because each person gets their own term. And so if we have one person, it's just that. If we have, or n equals 1. If we have 3 people, n equals 3, etc. And then we would multiply by 365 times 364 times 363 times etc. up until the point where we get to 365 minus n minus 1. And so it's n minus 1, where n, again, is the total number of people, minus 1, because we are starting, we're starting at 365 rather than 364. So basically, with one person, you don't want to subtract anything from 365, so you'll get 1 minus 1 is 0, equals 365. If you have 2 people, you get 2 minus 1, and so 365 minus 1 is 364, etc. So this is going to be your last term, and I've just generalized it for n number of people. And so what this means is that now we can see that the probability of finding 2 folks with a different birthday is exponential, which means that it changes like that. And so the first few terms are not going to change very much, but then all of a sudden it changes very quickly. And so if we were to calculate this for 23 people, let's say n equals 23, our equation would be 1 over 365 to the 23rd times, 365 times 364 times 363 times 362 times, oh my gosh, all the way to, what is that? 365 minus 23 to 342 times times 342. So you have to multiply all of those terms together. There's a bunch that I left out because, again, I am lazy. I don't want to write them all out. But if you were to do this on your calculator, you would get that this probability is about 49%. And so now we're like, wait a second, we're at 50%. So in this case, if we have 23 people in the room, the probability that we find 2 people, again, doesn't have to be me, 2 random people with the same birthday is 1 minus 49% with n equals 23, and 1 minus 49% is 51%. That's pretty wild, right? I love this stuff because all of a sudden we're like, oh my gosh, you only need 23 people in a room to have a 50% chance, 51% chance of finding 2 folks with the same birthday. So fascinating. I love that. And it turns out if you go all the way up to 75 people, it's a 99.9% chance that you will find 2 people with the same birthday. So if you happen to find yourself at a really big rager, a really big party, then you should definitely try and find 2 folks with the same birthday. It's a really fun party trick and a great way to make friends. Yeah. Okay. So please check this for yourself because I think it's really powerful when you can do the math and you can see how it works out. And of course, let me know if you have any questions on this. I know we just did a deep dive into probability and you might just be like, "Wah!" That's okay. If it's confusing the first time, watch it again, rewatch it, do the calculations, and if there are any questions that you still have, please, please, please leave a comment and we can tackle it together. All right, thanks very much for watching, and we'll see you next time when we return with our regularly scheduled algebra programming. Bye!